All right, ladies and gentlemen, let's take a look at this aldehyde slash ketone acetal conversion again. So if you have a the ketone and you can the convert to its ether form if the reaction is if you provide acetic acid as a catalyst. So the equilibrium, the direction of the equilibrium can be controlled by Le Chatelier's principle. So if you want the carbonyl form, then you add a lot of water. If you want the ether form, acetate, okay, we can add more alcohol. Okay, so these two forms has distinctly different reactivities. In the carbonyl form, the carbonyl carbon is electrophilic, carbonyl oxygen is nucleophilic. In the ether form, this carbon is considered unreactive, except you treat it with concentrated hot hydrogen halide. Okay, that's so basically we can manipulate the reactivity of carbonyl group. Okay, so what's the value of us having the ability to change the the reactivity of carbonyl group, and this can be best illustrated by this example. So assume you have this compound. This compound has two key functional groups. One is the ketone carbonyl, the other one is a terminal alkyne. So assume that you are given a task to replace this terminal alkyne. Basically, you need to alkylate, okay, this triple bond, alkylate it, okay. So from what we learned in organic 1, this alkylation can be done by treating this terminal alkyne with sodium amide, because this proton is kind of acidic. Using sodium amide can convert it, okay, into using sodium amide can convert this one into this, okay? And once it convert to this, you could throw in some methyl iodide. Okay, reaction happens, right? It seems like a very simple task, but what's the problem here? If you really directly treat this compound with sodium amide, and this conjugated base of terminal alkyne, as we know, is highly nucleophilic. Okay? If it's highly nucleophilic, not only can react with alkyl halide, it can react even faster with this electrophilic carbonyl carbon. And we actually saw this reaction in chapter 15. And I hope you recall, if you have this carbonyl group, you can have this one, okay, then nucleophilic attack this, okay, give you then you protonate it, you get alcohol, okay. So that means if you directly have this compound with both carbonyl group and the terminal alkyne, if you treat with sodium amide, you will not have this product, okay, because of this one will react with own carbonyl. Okay, so to solve the problem, you have to protect this carbonyl group, make it not capable of reacting with nucleophilic this conjugated base of alkyne. This is called protection process. Okay, so how do we protect it? We just convert this carbonyl group to its keto form. And you know keto form is ether. It's technically ether. And ether won't react with anything other than concentrated hydrogen halide. And usually only happen at a hot environment, okay? Not even room temperature. So that's how do we do the protection. We throw in some alcohol, okay, to encourage the keto formation, because we know this is a ketone, right? Ketone usually does not want to react with regular alcohol, give you keto, okay? So you need you know, this one, 1,2-diol, okay? 1,2-diol, if using this ethylene glycol, the keto will be a 5-membered ring. It will give you additional motivation for the keto to form. Okay? So that's why we're choosing this particular alcohol. Okay, and then at the same time, this ethylene glycol is very cheap. So why not? Okay? It's cheap alcohol, and and also can promote the formation of the acetal. And the p-toluene sulfonic acid is a catalyst. Benzene is just to shift the equilibrium to the keto side. Benzene is help remove water. Okay, and this can give us the keto form in pretty high yield, 80%. Then once the carbonyl group is converted to keto form, will no longer react with any normal nucleophiles, okay, unless it's a hydrogen halide. Okay. So then you can treat with sodium amide in ammonia. You can get this conjugate base of terminal alkyne. Then you alkylate it, okay. You get to the finished alkylation. Now, if you want a carbonyl group back, how do you do that? You want to eventually want carbonyl back. How do you do that? Tons of water and what? Just water. The reaction may not be fast enough. Acid. Okay. Tons of water and acid. Then you get a carbonyl form back. So that's why you do. Okay. That's this one strategy. Okay. If you are doing one part, if your goal is to change the functional group of one part of the molecule, but the other part of the molecule have a functional group may interfere your reaction, you can convert to something not reacting under the reaction condition, and then you can bring it back later on. This is called protection, deep protection method. Okay. Yes.
Then organic acid is that only use with the benzene, nothing else that we don't.
Oh, could you say your question again?
So if we're gonna use that acid, right? The
acid.
Yeah. So it only used with the benzene, and any other case would be with the any other acid. We only need to use this acid with the benzene in organic.
Oh, the acid is just for better solubility. So in organic solvent, it's under the benzene to remove water.
Yeah, I know, but when is this acid used compared to the other? Like you see.
Oh, okay. So why we don't using HCl here? Because HCl is a volatile acid. So if you do HCl, then you can evaporate away. Okay? Because you're doing distillation here. HCl will be distilled away. So you want the acid strong enough, dissolving organic solvent, and also doesn't want to boil easily. Okay? So that's why we're using this acid. You can use sulfuric acid also, but sulfuric acid may have solubility. You said if you're in a reaction, you just use sulfuric acid, nothing wrong. Technically it works. Just solubility is a bit worse. Okay? So just don't use hydrochloric acid here because in my example, if you're doing it, you need to do distillation, distill water away, then hydrochloric acid will be distilled away. Then it won't work very well. Okay? But if you want to use ketone and sulfonic acid, second step is perfectly fine. Okay. So you can use ketone and sulfonic acid all the way in the first and second step because this just provides acidity environment. And it's shown as well. Sulfuric acid, the peak sulfuric acid. If you want to simplify the type of memorize it, oh, peak sulfuric acid all the way, no problem. The second one we're using HCl is because it's cheaper than this. Okay? In real world, it's cheaper. Okay? And we don't worry about evaporation. We're not doing distillation. So this is one important strategy organic chemistry. Guaranteed will be tested next week. Okay, guaranteed. Okay, this is an important strategy. So you need to have knowledge about it. Okay? Any questions about either the addition of alcohol to carbonyl and this protection strategy? Okay, if not, we look at the next, the nucleophilic addition to carbonyl. So far we look at the 3 nucleophilic addition to carbonyl. One is hydration, one is cyanohydrogen formation. These 2 additions pretty simple. No further reaction after the addition reaction. Okay? No further reaction after addition reaction. But when we carry out nucleophilic addition of alcohol to the carbonyl group, we see that after first nucleophilic addition, if the reaction carry out acidic environment, we actually see this one first stage, okay, is just nucleophilic addition, acid nucleophilic addition. Second stage is SN1 actually. Okay, so you could the addition product could further undergo reaction. Okay? So we're going to see another example. Okay, you will see additional. Basically, you'll see 2 stages of reaction. First stage is nucleophilic addition. Okay, just like all the nucleophilic addition we have seen so far, the nucleophilic part added to the carbonyl carbon, the electrophilic part added to carbonyl oxygen. So here the nucleophile is an amine, and we will discuss this class of compound in greater detail at the later part of the semester. But just like water, alcohol, okay, I'm gonna write, and hydrogen cyanide, I'm gonna write the amine into 2 fragments. Okay, so just as usual, because of hydrogen has a lower electron activity than the nitrogen, right? So we consider hydrogen nitrogen bond is a polarized bond, polar bond, not very highly polar, but reasonable polarity. So we say, oh, proton is a positive polarized, and the nitrogen is negative polarized. Okay, so we write as this. So we can look at this amine as 2 fragments. One is the electrophilic part, the red proton, electrophilic part. Remaining part is nucleophilic part, right? Blue part. Okay. So if you undergo nucleophilic addition, the proton, this one goes to the carbonyl oxygen, and the blue part, nucleophilic part, add to carbonyl carbon. Any question about that? Just say it's different from, could it be different from the 2 R's in the people? Could be different. Okay. That also could be the same. Okay. That could be different from the 2 R's, R prime. Okay. They're different. They could be different. Any question about this step? Same as water, hydrogen cyanide, alcohol added to the carbonyl carbon. Addition step. Okay. Yeah.
You didn't share the screen.
Really?
Yeah.
Oh, okay. I thought I did. Okay. So, any question about first stage? Okay. Those. It's a standard nucleophilic addition. Okay. Under the Second stage is different from the reaction with alcohol. Instead of SN1, we're going to have one E1 or E2, depend on the exact reaction, but it's most likely the E1, as you're going to see, E1, okay? First thing, in terms of I want to compare, the addition rate of amine to carbonyl compound under the addition rate to the to same compound, let's say. So if you compare, if you have same carbonyl compound, react with water, okay, and amine, which reaction will be faster? Say both reaction, no catalyst are provided, assume, okay? Which one will be faster? Same electrophiles, say acetone, okay? And the one react with water, the other react with, let's say, a random amine, say, which one will be, which reaction will be faster? Water and this random amine, which one will be faster? We have the same electrophile, okay? The really question is which nucleophile is more powerful? Which one is more powerful? The amine is more powerful, okay? Why the amine is more powerful? Because water, oxygen nucleophile attacking atom, and amine, nitrogen nucleophile attacking atom. Both are neutral nucleophiles, okay? So when it comes to charge, they are comparable, okay? Now it really depends on which atom, okay, is more willing to give out that lone pair, because both cases are using lone pair to attack, right? Both pairs using lone pair to attack. Which atom is more willing to give out the lone pair? Is the atom is less electronegative, will be more willing to give out lone pair. And nitrogen electronegativity is about 0.5 units lower than oxygen. So that makes nitrogen substantially more willing to give out the lone pair. So makes this amine much more nucleophilic than water. How much more nucleophilic? Again, check that table, chapter 6. Okay, I told many times, chapter 6, that table, about 1,000 times more nucleophilic. So the amine reaction with carbonyl don't need a catalyst. 1,000 times faster by itself, no catalyst needed. Okay, the typical amine is really fast usually. Okay. So if you have a compound both with amine and the OH group in the in the same nucleophile, then which one will be reacting? Let's say if I have this okay, and I have this nucleophile, okay? This nucleophile, left side nucleophile has two types of nucleophilic atom, N or O. So if just don't have any catalyst, just mix these two guys, let them react. The major product will be the more nucleophilic atom react with the carbonyl compound. So which atom is more nucleophilic? Nitrogen or oxygen? How many of them say nitrogen is more nucleophilic? 1, 2, 3, 4, 5. How many say oxygen more nucleophilic? Nobody. Okay. So most of them say no opinion. Nitrogen is more nucleophilic because of low electron activity. Okay, more willing to low electron activity means less ability to hold the lone pair to itself, more willing to give up. So in this case, if no catalyst at all, you will see the nitrogen, okay, will be added to the carbonyl carbon. So that is the first step product. Okay. And if you have two hydrogen bound to the amine, we call the primary amine. We can briefly mention the classification of amines, and although we're going to discuss this thing in great detail, in a later chapter. So if you have this thing, we call primary amine, meaning nitrogen only direct bound to a single carbon. It's called primary amine. And if you have this thing, we call the secondary amine, because nitrogen is directly bound to two carbons. Okay, and if you have this we call tertiary amine. Okay, this is some the brief classification. And if you have a primary amine, this nucleophilic addition product, okay, will further undergo elimination, and give you imine. Basically, you're gonna lose a molecule of water, okay, give you a product of the the CN double bond. And this reaction, just like similar to that, the acetal formation is reversible. So, but the reaction can be driven, by applying Le Chatelier's principle. So if you have a means to remove water, you're going to have imine as a major product. So let me just give you some example of such reactions. Say if you have this one react with this reaction doesn't really need a catalyst. Just you heat a bit, you will become this. Okay, this is called imine. Okay, have a basic what happens is that you can consider the nucleophilic nitrogen atom replace nucleophilic oxygen atom, give you a C. Originally you have CO double bond, you become CN double bond. Yes, you have a question? And this reaction can actually happen with a number of other compounds with NH2 groups. Okay, so this one can give, again, if you heat it, it can give you the. So basically, you will see all the NH2 will react with the CO double bond, become CN double bond. Okay, and another example. You might have seen this one. You might need to use this kind of reaction in the organic lab. Okay, obviously all those reactions form water. Okay, so what is the mechanism of this type of reaction? Okay, so the reaction have the the two stages. As I showed you earlier, first nucleophilic addition, second is elimination. So in the first stage, the rate limited step is how the nuclear bomb attack the carbonyl carbon. So this because of nitrogen, amine is about 1,000 times more nucleophilic than alcohol and water. So this reaction usually doesn't require catalysis. So just mixing the amine and the aldehyde or ketone, the reaction will happen. So the is basic nitrogen attacks the carbon electrophilic carbonyl carbon, then the CO bond opens, and then you have a dipolar intermediate is both cation and anion, and that's the just a rate limiting step. Then this bipolar substance can undergo proton transfer. The proton transfer could be intramolecular, could be intermolecular. Here we're just using the example showing is intermolecular. So the they basically give you a neutral addition product, hemiacetal. Okay, so that is a nucleophilic addition product. You don't have to have two water molecules involved. Okay, you can say, okay, this oxygen alkoxide directly extract the proton from here, also fine. Okay, either way. Okay, but this is nucleophilic addition product. Then this guy, okay, have the two nucleophilic atoms, the nitrogen and oxygen. So the both nucleophilic atoms can be protonated, and if you think about which atom is more basic, is nitrogen more basic or oxygen more basic? Just based on the knowledge you learned in general chemistry, is nitrogen atom more basic, oxygen atom more basic? The key part, thank you, that's correct answer. Nitrogen is more basic. Why is nitrogen more basic? Because the basicity depends on how well the lone pair, okay, wants to be given out. Again, nitrogen lone pair is held, okay, weaker to the nitrogen atom, so it's more easy to give out. Nitrogen is more basic. But if a protonation of nitrogen going back to the, first stage reaction, okay, go back to the starting material, so it's not productive. So we don't need to worry about nitrogen being protonated. We only consider what if oxygen is protonated, okay? And when oxygen is protonated, you have water. And if you see water immediately, okay, water is an excellent leaving group. So then next step, water leaves, give you a carbocation, okay? And this carbocation is exceptionally stable carbocation. Why? Because this nitrogen lone pair can happily stabilize this positive charge, give you this resonance form. And this resonance form is even more stable than this resonance form, this one. Okay, why? Because nitrogen is less electronegative than oxygen. Okay, so it's happier to nitrogen to carry the positive charge. Okay, so that makes this kind of ionization process even easier than the protonated hemiacetal. Okay, so then then after this carbocation forms, okay, then the carbocation can lose this carbocation, right? And this is this alpha carbon. This is a beta atom, not a beta carbon, beta nitrogen. Okay, so then the water can take the beta proton away from nitrogen, give you the carbon nitrogen bond. And keep in mind, if a compound has both beta proton from the, let's say, if you have this, assume if you have this, if you have this carbocation, okay, which which elimination is most possible? You have the actually 3 types of beta protons. Okay, let's say you have black beta proton, you have a red beta proton, you also have this green beta proton. Okay, So which beta proton is most likely to leave? If the reaction is controlled, okay, by kinetics, which proton is most likely to leave depends on which proton is most acidic. Okay, so out of those three protons, the red one, green one, black one, which one is most acidic? Black one, the green one, and any argument that makes them acidity different? They are similar. Okay, they are both are carbon hydrogen bond. So only the nitrogen hydrogen bond is most polar bond. So it's most acidic. So when both the beta proton or nitrogen carbon both are available, they will probably be leaving from the nitrogen because most acidic. Okay? So it's easiest to leave. So this is the argument why when both CC bond and CN double bond can form, will form CN double. Okay? Because of its formation is easier. Huh? Up? Okay. All right, gonna see you guys Wednesday. And the likely the exam, next exam will be given as scheduled next Monday, basically.
No.